In the 60s, Nobel Prize-winning physicist Luis Alvarez oversaw the assembly of a huge scientific apparatus inside the ancient Egyptian pyramid of Khafre in Giza. His goal? To search for a chamber deep within the structure, which, if it existed, would have been hidden for thousands of years. Not for the tantalizing possibility of riches contained within, no, but to demonstrate the effectiveness of a new technology designed to see inside thick materials. A technology that is analogous to, but much more effective than, X-ray imaging. This technique, in fact, used muons, a cousin of the electron, tiny particles which rain down on us constantly but invisibly from the heavens. Muons are created as a result of high-energy particles originating in the explosions of dying stars many light years away in space, colliding with atoms in the upper atmosphere. In ancient Egyptian myth, the souls of dead pharaohs would rise to the heavens to form new stars. Today, we use particles ejected from dying stars to peer inside their secreted tombs. The tallest pyramid of Giza, and indeed the world, was built for Pharaoh Khufu in the 26th century BC, the Great Pyramid. His son, Khafre, is next door, 4 meters shorter, but is superficially almost identical, save for the remaining cladding at the top. But as any budding Egyptologist, or decent human being, knows, what is most important is on the inside. The Father Khufu's pyramid has a complicated interior, housing not just a chamber for the pharaoh himself, but a series of other voids and tunnels, some of which have been known for thousands of years. Today, we believe the architecture of his pyramid was the culmination of a design philosophy which saw increasingly more elaborate interiors over the 4th dynasty. But his son, Khafre, has a tomb which is much more stripped back. A single main room for him to be laid to rest. And that's pretty much it. Who said minimalism is a new idea? Egyptologists have for some time marked the difference between father and son's tombs down to as simply one of ease of construction. Complex interiors are much harder to build than more modest ones. More empty space in the structure means a greater risk of collapse. But for some, amateurs, not experts mind, the case is not so cut and dry. Is there some hidden cavity in the son's pyramid? Some lost treasure, sealed away for millennia, awaiting its discovery by a plucky Indiana Jones type? The call of the unknown is intoxicating to some, and maddening to a select few. For most of history, the method to confirm the existence of a hypothesized tomb is tantamount to breaking and entering. Grave robbery, perhaps. Muon tomography, the technique Luis Alvarez was pioneering, held the promise of being able to peer inside a pyramid, or the earth, or a hurricane, remotely. And what's even better, the technology is entirely passive, as opposed to X-rays. X-rays, for the record, cannot penetrate rock like this. All the muon detector did, humming away in the burial chamber of Khafre some 4.5 millennia after its sealing away for the first time, was to detect particles, muons, which were already streaming through the rock. All Alvarez wanted to do was to detect them and the patterns held within, almost like magic. By measuring the amount of muons the detectors pick up from various positions and angles around the object, scientists can build an image of the interior. Since muons are more likely to decay when passing through dense materials, when more or less muons are detected than predicted coming through a material, rock, ice, cloud, whatever, it hints at an inhomogeneous interior. Something hidden. For a pyramid, this may be a cavity, a tomb. For a cyclone, it may be an area of greater particulate matter, and for a volcano, it may indicate the presence of magma. For Luis Alvarez, this technique failed to confirm the existence of a new tomb. It really does seem there is no hidden treasures to be found in Khafre's pyramid. The technique has, however, gone mainstream and is being used to predict volcano eruptions by seeing the way magma is flowing internally, and a new way to measure and predict the weather. This technology is starting to be deployed to help or even save human lives. That's not the end of it. In the late 2010s, the technique was turned on Khufu's tomb, the Great Pyramid, and they found a cavity. a cavity that was previously only known by the labourers and architects of this ancient tomb. Despite tomb raiders and endless tourists walking up the grand gallery beneath it, the 30 to 40 metre long Scan Pyramid's Big Void, as it is currently known, took the power of muon tomography to unveil it. Big Void may be a hidden burial tomb, or it may be a cavity left empty for structural reasons. A planned new study using much more sensitive detectors may clear this up in coming years. The purpose of the void is still under question, but the validity of muon tomography is certain. So, what are muons? Let's trace back the path of a single muon, one of many that was detected. A muon is like the bigger brother of an electron, a particle that is part of every atom in everything you can see or touch. A muon is heavier than the electron, but it also has a minute lifetime. Electrons last forever, whereas a muon lives for around 2 millionths of a second. When they die or decay, they turn into electrons or neutrinos. The discovery of the muon in the early 20th century was a surprise. Scientists already knew of all the subatomic ingredients of the world we live in, but as more new subatomic particles were discovered, particles that are entirely unused in the world as we experience it, the physicist I. Rabi famously quipped, "Who ordered that?" It's safe to say muons have a tiny lifetime. However, if you make the simple calculation of how deep into our atmosphere they should penetrate, you find that they decay far too quickly to hit the ground in the numbers we measure. The catch, like so many other things in physics, is down to Einstein. When moving close to the speed of light, like our muon, things behave weirdly. The universe treats the speed of light as absolute, not time or distance. It's perfectly possible for two objective observers to measure the same thing and get different answers, at least when it comes to duration or length. While the reason for this is too difficult to get into here, the upshot is our muon experiences a squashed universe due to its immense speed. The atmosphere, and indeed the entire Earth, is extremely thin from its perspective. A muon can travel much further through this thinner, squashed atmosphere than it otherwise could, allowing them to reach ground level in numbers to be detectable. Muons are formed when high-energy particles collide with the upper atmosphere. These high-energy particles are known as cosmic rays, and their journeys take them huge distances, originating far outside the solar system, even from other galaxies in some cases. The high-energy particle in question was formed in the explosion at the end of a large star's life, a supernova. It's entirely possible that the event that triggered a cosmic ray that led to a muon detection in Khufu's pyramid happened at the same time the pharaoh was alive, 4,500 years ago, 4,500 light years away. By capturing the muon flux, amount of radiation detected, and the direction the particles were travelling, we can construct an image much like your eye does with light. The image shows where muons pass easily or with some difficulty, and with detections from different locations, we can construct a 3D image of a material's interior. This is the basis of muon tomography. The mass of the muon is the basis of its power. Being 207 times heavier than an electron, it is not only able to pass through kilometers of rock, it also does so with straight paths. As scientists can be confident about the path it was travelling along, they can accurately construct images of interior spaces they detect. Ancient Egyptians believed that the sun was personified by the god Ra, head of a falcon. That the sun was recreated each morning with the help of a scarab beetle god, Khepri. Every night, as the sun disappeared behind the horizon, Ra would battle and win against the serpent lord of chaos, Apep, rising once again the next day. It seems quaint and nonsensical to us today. But ancient Egyptians were also keen sky watchers and cataloguers of stars in the night's sky. Egyptians used the stars to mark the new year and the calendar and to tell the time at night with their own system of constellations. The pyramids were built with remarkable planning and foresight. They align with the cardinal directions, demonstrate remarkable tolerances, let alone the enormous manpower required to create them. Just like today, ancient Egyptian culture shows a mix of stunning intellectual and engineering achievement and a rich mythology detached from reality. Exactly where the borders between each domain lie may only be seen in retrospect, a fact that is as true for them as it is for us. And we both still worship cats. Muon tomography is an emerging technology which is letting us, for the first time, truly understand the insides of certain big things to uncover truths which we previously could only speculate and imagine. But one rung on a ladder of scientific and technological development. How will future humans look back at our stories, our theories and our constructs today? What will seem obviously correct? What will seem absurd? And what will leave them scratching their heads? Remember to like, subscribe and leave a comment. Thanks for watching.